Hello, good morning. So we continue from where we stopped last week. So this is what we are going to be looking at. This will take us 2 weeks. So today we shall be looking at equilibrium phase diagram. So what do you mean by equilibrium phase diagram? So it's a diagram that represents relationship between temperature, pressure, and composition, right? And the quantities of phases at equilibrium. Many microstructures develop from phase transformations, the changes that occur between phases when temperature is altered. So this may involve transition from one phase to another, or appearance of another, or appearance or disappearance of a phase. So this is helpful in predicting phase transformations and resulting microstructure, which may have equilibrium or non-equilibrium characters. I think last week we have started something like that. This is a phase diagram. Can you see a copper nickel? So transition from here, the liquid phase and the solid phase. So this is temperature and this is composition. So here is saying that it's 100% nickel. It means we are varying nickel, right? With copper. Here at 0 here it means copper is 100%, and at 100% nickel it means copper is 0% what? Copper. So here there's a transition from liquid to solid. This solid is alpha. In today's one here we are saying temperature, pressure, and composition. In most cases, these are three parameters, right? So in most cases, we keep one constant and we vary the others. So for example, like in the one I just treated, if you vary temperature and composition, it means at a constant what? At constant pressure. Or for example, if you vary temperature and pressure, it means at constant what? Composition. Out of these three components, it's easy for you in a 2D diagram to vary two parameters, right? Two factors. It means you can vary two factors and keep the other factor what? Constant. Except if you are doing a 3D analysis or you are doing a 3D modeling, then you can be able to vary all the three parameters at the same time. So this is basically what it is, and it says the appearance and disappearance of phases. You can see for the last example here, you can see here is liquid. There are three major regions here, isn't it? Alpha represents the solid, alpha plus liquid is another region, and then liquid is another what? Region. So let's see the types of equilibrium phase diagram we have. We have the unary phase diagram, and then we have the binary what? The phase diagram. This is where we are going to emphasize on the binary phase diagram. Are we all together? So let's start with the unary just for illustration, but this is where the unary is the one we have. We vary temperature and pressure and we keep composition constant, right? While the binary, we vary what? This is the binary we are going to concentrate on, while this is unary just for what? Illustration, right? Because in most cases where we are emphasizing, we are going to dwell more on the binary is we want to see how alloys, right? Composition of alloys as the temperature change. So we want to see the resulting microstructure. In that case, at constant what? Atmospheric pressure, isn't it? So let's start with the unary. Here we have pressure and temperature. It means at a constant what? Composition. It means here we are varying what? We are looking at change of phase of water as it's moved from liquid to solid and what? Vapor. So for a pure substance, this means the pressure and temperature are the variables, right? We cannot vary the composition of water, isn't it? It's already water itself, but then we want to see how it changes in phase. As an example here is water. So out of these three variables, temperature, pressure, and composition, it means we are keeping the composition constant, right? And so it means you can vary it. So as we vary pressure and temperature for water, you see we will have several regions. We have three major regions: solid, liquid, and water. For example, at 1 atmosphere during heating, that's the pressure. At 1 atmospheric pressure, you can have a change from solid to what? To liquid phase. At O here, this is where we'll have all the three phases coexist at equilibrium. So at O here it means they coexist. Solid, liquid, and vapor. So next, let's look at the binary. as I say, is the most important. We have different types. So we start with the first one, binary isomorphous phase diagram. So this is it. In this case, we'll have what? Liquid, solid plus liquid, and then what? And liquid, solid phase. So I've explained this even before we started this. This is exactly what I'm saying. I think I started this last week. So this is the solid phase. Can you see I'm shading it in yellow? We call that alpha. And this is the combination. This is the liquid state. This is the liquid in blue shading. And this is the combination of liquid plus what? Liquid plus solid, isn't it? So we have three regions: liquid, solid represented by alpha, and then you have solid plus liquid. So in this case, we can call this a kind of sticky what? It's not solid and it's not liquid. You call that sticky region, right? Or you call it a dual region because there are two phases there. And in this case, we call them single because it's only one. The liquid is homogeneous, right? And the solid is also single what? Single regions. And here we either call it sticky or dual regions. So why this is important? Because all through here it means copper. When you are combining copper and nickel to form an alloy, both copper and nickel, they are soluble in each other's, right? And so you don't see there is no limit to solubility. You can see at 0% copper, do you see any change in phase in the solid region? No. It's because what? Copper is soluble in what? Or nickel is soluble in copper. And we call that what? Isomorphous. Yes, right? Because both are soluble in each other's, we call them isomorphous. So there's no any restriction, no any solubility limit between copper and nickel. And we call copper nickel phase diagram, we call it isomorphous, soluble in each other's. Right. So next we see, already I've explained this is the liquid region. You see the temperature, and there's always temperature at which there is a change in phase. So for example, if your composition here is 20, it means here we look at is what percentage of nickel? 20% nickel. When you have 20% nickel, what is the percentage of copper? Yes, 80%. So here at 0% copper, it means it's pure copper. Here 10% copper means 90% nickel. And up to here, you have 100% what? Nickel and 0% copper. And so this phase diagram gives us a kind of microstructure of alloys, right? As you vary the two materials. I've explained last week that what is an alloy? An alloy, first, there must be a metal, right? And then an addition of what? Either a non-metal or another metal. So in this case, we have two metals, right, to form an alloy. So in this case, already we have three different phases: alpha, liquid, and alpha plus liquid region. So let's see, how do we interpret this phase diagram? So let's start. The most important thing here is the phases that are present. Already we know that the composition of these phases, and then the percentage fraction of these what? Phases. So let's start with the phases present. So for this one, how many phases are present? We have three phases. So for example, if I have an alloy here, A, what does it mean? What is the phase? A is at what phase? This is our alpha region and alpha plus liquid. This is temperature and this is composition. Let's assume here is 60 and here is what? 80. 60, 40, and 20. Here, whatever is written here is what is being varied. Sometimes it can be written percentage weight or percentage what? Volume. But in this case, let's look at it. What was written there? Is percentage weight of nickel, right? So let's assume at point A, what is this alloy? So can someone tell me at point A, what is this alloy? For example, alloy, you can at point A, what is the alloy liquid or solid? Let me call this A. Is it solid or liquid? Because we want to see how we can identify these phases. Yeah, solid. So A is solid. Then the second question is, what's the composition of A? The composition of the phase. What is the composition of this alloy? You know, this is an alloy of what? So what's the composition? Alloy of what approximately? What is the composition of this alloy? Yes, so the composition is 60% by weight nickel and also 40% by weight what? Copper. So this is the composition of this alloy. So this is an alloy of 60% nickel and 40% what? Copper. So in this case, what is the percentage fraction? In this case, we don't have that because it's completely solid, isn't it? So in this case, we don't have percentage fraction because it's completely what? Solid. If, for example, it is in this region, solid plus liquid, then we have to know what is the percentage fraction of the solid and what is the percentage fraction of the what? Liquid. Present. So for example, let's look at B. You know, B is a combination of liquid and solid, right? So in this case, we have to determine. So there's another point B. We call this point B. So what is the phase present for B? Yes, liquid and solid. So now I'll ask you, what is the composition? So how do we determine this composition? In this case, we will have to draw what we call a tie line and determine the composition straight away. The alloy B itself is a combination of what? So you drag down here, isn't it that for A? So what is the composition of alloy B? You said approximately what? Is about 30% nickel and then 70. You have to start with nickel because nickel is the one being varied, and then 70% what? Copper. Right. So now we want to see what happens at point B. For an alloy B, composition of liquid. So in this case, we have to draw a tie line first. Look at, you draw a horizontal line. That is called the tie line, right? B itself has a composition of this C0, which is approximately 34-35% nickel. And how many percent copper? 65, right? You first draw a tie line, and then where it touches the upper and the lower here, where it touches the solid boundary, you know, alpha is the solid boundary, so we call that what? When you drag it down, this gives you the composition of the solid. This gives you the composition of the what? Liquid. You know, here is the combination of solid and liquid, right? What is the composition of the liquid? It means after drawing this horizontal line, where it touches this, you call it L, the liquid boundary line. The liquid boundary line and the solid boundary line. So where it touches the liquid boundary line, you drag it down. That is the composition of the what? Liquid. And in that case, you have it at 2% by weight nickel. You know, at every point you have nickel and copper, isn't it? So it's at 2% nickel, and then when you subtract the remaining from 100, you will have 68% what? Copper. The composition of the solid is what? This alpha. When you drag it down, you will have approximately 43% by weight nickel, and then the other is copper, isn't it? Which is, the remainder is 57% by weight what? Copper. So this only show you, this L here and N only shows you the composition of the solid. You know, the solid will also have its composition, isn't it? Liquid will also have, at any point, liquid will have two compositions, solid, nickel and copper, right? Solid also will have two compositions, solid and copper. Are we together? So lastly now, so this is the composition of B. B is the composition of what? This, or else if you want to just give the composition of the B as an alloy, it is just C0. But if you want to give B a composition of B as component of the solid and liquid, then you will have to use this. The alpha itself will contain solid nickel and copper, and the liquid itself will contain what? Nickel and copper. So lastly is the percentage fraction. So in this case, we are not after composition of the solid and liquid, right? We want to see what percentage of it is solid, what percentage of it is liquid. So in this case, we designate this S, distance from B to the solid boundary S, and distance from B to the liquid boundary as R. So now we want to see what is the weight fraction of the liquid. This is it here. The liquid is going to be what? S all over total. So you won't take R. You know, the distance from the B to the liquid is R, isn't it? So you won't take R, you take S. So it's going to be S all over what? The total. And what is the total distance? R plus S. You can come here and say, okay, what is R, what is S? So R is what? C0, C alpha here means composition of the alpha. Here C0 is that of the alloy. C0 is that of the alloy. how you get the best approximate, and then also here Cl is that of the liquid. It's just a designation, right? Symbol. So in that case, you can compute. So in this case, C alpha approximately is going to be what? 42.5. Cl is approximately going to be what? 31.5. And C what? The alloy itself is going to be what? The alloy itself is liquid and solid. So in that case, it's going to be 35. So in that case, the composition of the liquid now is 0.68, which is about 68%. So even from here, you know that composition of the liquid is greater than that of the solid, right? It means liquid is 68%. And so you can also do for the alpha, similar way here. When you come, the distance from the B to the alpha is what? To the solid is S, right? You won't take S, you take what? For the solid, you take the other one, which is R. Yes, R all over the total. R plus S. Yes, so and you come and what is the value of R here? Is C naught minus CL. And C naught is what? 35. And CL is what? 31.5. And the total is here is 42.5 minus CL. So in that case, so even from the first question, you can decide to know the other one is just 1 minus 0.68 or 100 minus 68%. But then when you do for both, then you can confirm the accuracy of your what? Of your result. So this is the description, how you can determine it. Here, when you have two binary solids, when you have two compositions, for example, we are going to look at that. What we just discussed here is binary but isomorphous. So we are going to look at binary eutectic. So here is development of microstructure. It means movement from what? From liquid to solid plus liquid, and then from what? And then to solid, right? So this is how the microstructure is developed. Here it's initially solid. When it touches this boundary, the liquid boundary is virtually what? Liquid. But then solid begins to what? Appear. As you move down, solid, more solid is appearing, and here is virtually solid, but they still what? Liquid. At the boundary here is virtually liquid, and here is virtually solid. So the moment you cross this line, then it becomes fully what? Solid. And also remember that all this depends on the temperature, right? At various temperatures, as you are going down, temperature changes. That's cooling. So this is the advantage of alloying. You can see the tensile strength of copper is about what? Pure copper is about, look at my arrow, 230. So by the time you begin to add 20% nickel, you can see the strength has increased from 230 to almost 3 watts, 340. When you add 40% nickel, you can see to almost 400. And you have the highest at 60% nickel, which is about 420. So you can see it's almost more than almost double the. So why do you need copper? When you add nickel to copper, you can have much higher strength. And you can see also here the tensile strength of pure nickel is about 350. Can you look at the right hand side? Drag it. This is pure nickel, which is 100%. At the other right hand side, right? Don't use this unit is the older unit, is the imperial unit. So if you drag this 50 here, you will have about 320 in terms of the imperial. Here is in terms of the metric unit, tensile strength of pure nickel is about 350. So if you want to increase this, you can add copper. Adding copper up to 40% to nickel, you will have almost what? The highest strength. But then the problem here is ductility goes down. Can you see? So it's a trade-off. If ductility is not a major issue for you, you need high strength, then you can, get the highest strength. But even though at lowest ductility is still about 30%. Copper is very ductile, and likewise nickel. Though copper is more ductile than nickel, copper is about 65% is ductility, right? While nickel is about 50%. So you see advantage why alloys are used in engineering predominantly because pure metals themselves do not possess the required strength, right? So in this case, it's better you alloy them. We are going to also look at iron carbon. In this case, where carbon is alloyed to what? Iron. So next is the binary eutectic. So this is what we call binary eutectic. This is called binary eutectic. And this is where we call the eutectic here. Is the medium is lead and tin. So lead has higher melting temperature than tin. So this is what we mean by binary eutectic. You can see it's different from the other one. In this case, we have liquid region here, L. We have two solid region, alpha plus what, and beta. Can you see two solid region? And then any movement you do, for example, I'm going this way, it's going to be alpha plus what? Liquid. Where you have a region in between, then when you have liquid and then you have alpha, you can cross this into alpha, isn't it? Or you can cross from alpha to liquid. Then what is in between is going to be the product of the two. So for example, when you are crossing this way, so what is going to be in between? Or when I'm crossing this way, or when I'm crossing what? So the in between here is going to be what? Alpha plus. In this case, what is going to be in between for alpha and beta here? Alpha plus what? Beta. And here is going to be alpha plus. Yes. So this is called eutectic. Why do you call it eutectic? This is eutectic region. Because if you look at it here, for example, if here is lead and here is tin, it means only small amount of lead. You can see here, let's assume here is 60%. Can you see? So it means only small amount of tin is soluble in what? In lead to have alpha, right? Can you see my mouse? And only small amount of lead is soluble in tin to have what? Beta. So we have how many single solutions? We have alpha, beta, and what you can say. So liquid also is what? Is a single region. But how about the dual? We have alpha plus beta, alpha plus liquid, and beta plus liquid. So in this case, what it means here, for example, if it's lead, it means the melting temperature of lead is higher than that of melting temperature of what? Tin. Can you see where I'm marking now is the melting temperature of where? Tin. Right? And then here where I'm marking here is the melting temperature of what? Of lead. But what's the minimum temperature at which it can the two alloys or the alloy can melt? Let's assume here you can at this point we call it eutectic. So it means when you have an alloy, it can have a lower melting point temperature of what? 185, right? But then the individual elements will have, let's assume here is 3, and the melting temperature of 327, and the melting temperature of tin is 223. And so in between, the minimum temperature you can turn it to liquid is what? At 61.9%, and which is at 183. So that's the minimum temperature at which you can what? Melt the alloy. So at this point we call it what? Eutectic. So we have different types of eutectic. We have lead, tin. We have silver, what? Copper, silver. So in this case, it means what it's telling us is that all through the solid region, these two materials are not all through soluble in each other's, right? So it means copper is only, for example, an example of this. It means silver is only soluble in some certain amount. Maximum percentage of silver that can be soluble in copper is about 8%. And even with that, it is at higher what? Temperature. Can you see at room temperature, silver is not soluble in what? In copper. Can you see the region? The region starts at almost around 400, isn't it? So here, because here is pure silver, 100% silver, it means this little amount region here will mean what? Small amount of copper, right? So it means, so in that case, because in this case we don't call it isomorphous because all through copper and silver are not soluble in each other's, it's in only small amounts. And so this line here shows that this is the limit to solubility of what? Copper in silver. And this is the solvers, which is the limit of solubility of silver in what? In copper. So in that case, they will appear as alpha plus what? Beta. So it's different from the one we treated earlier. And the calculation is still the same, right? Next week we are going to do the calculation, you see that it's the same. So let's look at the microstructural change here. Each microstructure depending on the what? On the alloy, right? So this is another different alloy here. C2 here, alloy C1, how you can move from liquid to what? Solid alpha plus beta. So there's going to be changes of microstructure from liquid to here. Solid begins to enter here. You have fully alpha, and as you come down here, beta begins to appear, right? Because the whole of this region is what? Alpha plus beta. So this is the only point at the eutectic where you have this particular structure, right? You can see the laminate structure of alpha and what? And beta. Please. So it means when we move leftward, what happens leftward? We'll have this same structure with additional what? You will have this structure plus more of alpha, and when you move to the right, you will have this same structure with more of what? Beta. So ultimately, you still all through this region is alpha plus beta, but then we have different types of beta and different types of what? Alpha. So this is it here. When you move to the left, you see we have that same structure plus what? Addition of these balls. These balls represent what? Alpha. So ultimately, the whole of this structure is alpha plus beta, isn't it? Let's assume alpha is blue and beta is red. So this is the only point we have what? This particular structure. At what point? At 61.9. Weight percentage what? 10. So now when we move to the right, what will happen? And when we move to the left, what will happen? So when we move to the left, we still have this structure. The left. So alpha, okay. So what I'm saying here, as you move to the left, you still have this big ball as what? You still have this same microstructure, alpha plus beta, plus additional what? The ball that looks like ball alpha. So you still have these two combinations, right? This is the combination you'll have. As you move to the right, you still have your alpha plus beta. Just like that's we call that eutectic, plus more of what? More of beta. Yes, so beta will appear at the red, is it the red ball? Additional beta, which is red ball, and the additional alpha, which is the blue ball. So this is how it will appear as you move. And when you move further away from this 61.9 to the end, all the blue will disappear. It will only be left with beta. Remember, as you are moving away from the center, for example, you are moving to the alpha side, the beta is always reducing, right? All these three, you categorize them as what? Is a combination of alpha plus what? Beta. But then we have different types of what? Alpha and different types of beta. So maybe next week we look at how we can make calculation, and this additional eutectic can be a what? A boundary line. Is it clear? So next week we look at these examples and we top it from there. So we've come to the end of the lecture. Any questions?